Hey everyone, in this episode of ITS Now, we'll be looking at what intelligent transport systems are. I'm Alistair, and this is ITS Now. Despite sounding like a futuristic mode of transport, intelligent transport systems, or ITS for short, are actually technologies and systems associated with the management, operation, and use of a broad range of transport modes and their interrelationship with other infrastructure. The scale and complexity of ITS solutions ranges from individual standalone applications through to highly intricate systems deployments. ITS applications are typically implemented to provide solutions to improve safety, increase capacity, inform users, and manage assets. ITS applications span air, sea, and land transport modes, including different forms of public transport and the interaction with each other. In a highways context, ITS applications are often grouped into urban and interurban categories. Urban implementations are, as the name implies, the technologies typically deployed in towns and cities, whilst the interurban category relates to technologies on motorways and trunk roads. In urban settings, ITS infrastructure often uses complex urban traffic control, or UTC systems, which bring together a range of traffic subsystems, including coordinating the operation of traffic signals across a city's road network using real-time data from an array of traffic sensors. Examples of additional UTC features include bus priority, interaction with real-time passenger information systems, journey time and parking information subsystems, and incorporate these with active traffic network features. Traffic signals are an example of how ubiquitous some elements of ITS infrastructure has become in our environment, so that the complexities and capabilities of these systems is often overlooked. So traffic signals exist to separate conflicting traffic by the division of time within the spatial constraints in a safe, efficient, and equitable manner. The term traffic is encompassing and refers to all users, including pedestrians, cyclists, equestrians, public transport, emergency services, and motorized vehicles. The inclusion of the word equitable in our definition above reminds us of the way in which the emphasis has changed over recent years when considering the requirements for a traffic signal installation. In the past, it was sometimes difficult to justify the inclusion of features into designs, such as pedestrian facilities, at some locations, because of a perceived lack of demand. Interurban applications on motorways have used technologies for many years to passively monitor activity on the highway. However, over the years, additional features have been added to assist in actively managing traffic. These range from informing users about current conditions so that they can make informed decisions about their journeys, such as automatically warning drivers of incidents using roadside variable message signs, through to compelling users to modify their driving, such as by implementing variable speed limits to smooth traffic flow and ramp metering to control the volume of traffic entering a motorway, or by using enforcement cameras to improve compliance with speed limits or closed lanes. Vehicle detection is a basic building block for gathering data relating to traffic. Many will be familiar with the outline of vehicle detection loops in our roads. These come in a variety of shapes and sizes depending on their use, and the standards of the country being used in, but include rectangles, chevrons, circles, diamonds, and even butterflies. Vehicle detection is not only used to determine the presence of vehicles, such as on the approach to traffic signals, but can also be used to generate a comprehensive data set associated with traffic flow, including vehicle speed, classification of vehicle type, headway between vehicles, etc. This example shows a motorway incident detection system that uses pairs of inductive loops in each lane to capture a range of data parameters and to automatically detect incidents and communicate these to the regional control center. Other associated systems often used on the roadside include meteorological systems to capture weather conditions. These are often used for winter maintenance activities and to measure specific parameters such as wind speed in exposed locations. Modern systems now have remote sensor capabilities to measure carriageway temperature and surface salinity to identify requirements for the application of grit or for snow clearance without the need for in-carriageway sensors. Other associated capabilities include air quality measurements that range from large, highly accurate systems that need to be housed in a dedicated container-sized structure, down to small Internet of Things sensors, which are often single-parameter battery-powered devices. The output from these systems can be used with traffic management systems to alter traffic flow in response to particular environmental issues. Road tolling is another great example of how ITS technologies have developed over recent years, now typically using automatic number plate recognition, or ANPR for short, or vehicle tags to achieve a free flow toll instead of making vehicles stop to pay in cash to use a tolled road or bridge. So how might roadside infrastructure change in response to connected and automated vehicles? Looking to the future, much has been made of the impact that connected and automated vehicles, or CAVs, will have on the requirement for supporting infrastructure. In the future, vehicles are likely to change beyond all recognition. However, the first part of this progression will be the provision of connectivity to vehicles. This will underpin the route to vehicle automation by allowing vehicles to communicate with other vehicles. This is called V2V. And to the highway infrastructure, this is referred to as V2X. Using these communications facilities, it will allow vehicles to warn other vehicles of safety conditions, such as if they have to stop suddenly, or to be informed of damage to the road network, such as a pothole. In the interim, it is probable that features to improve efficiency and safety through the provision of online information, which equip vehicles with computerized systems which assist the driver, like active cruise control and lane departure, will become increasingly sophisticated. The last example shows how technology might be incorporated within the core of the road itself to enhance the way in which different classes of road users might interact with each other. Hopefully you found that interesting. In the next few episodes of ITS Now, we'll be covering a range of ITS topics, so make sure you don't miss them. See you next time.